Okay, well, welcome everyone to today's Castro in the Classroom. My name is Jenny Lynch. I'm the Castro School Education Officer, and presenting for us today on the topic of space is Eromanga Adermann, who's a PhD student from here at the University of Sydney. So Eromanga will talk to you for a while, and she has some slides that she'll be talking to throughout the presentation. If you don't have them in front of you, hopefully you can see them on a screen in your room. Excellent, some people are showing us that they have them. Some of them might be a little bit out of order, but Eromanga will explain that as she goes along. Now, as we do go along, please note down any questions you have, and we'll have a few minutes for questions at the end. So I'd like to hand over to Eromanga. Thank you.
Okay. Hi everybody, I'm Eromanga, and today I'll be presenting Castro in the Classroom on the topic of space, and in particular I'll be focusing on the subtopic in the syllabus called a successful rocket launch. So before I do that, I'll just tell you a little bit about myself. So I was in high school from 2004 to 2009, and I did the HSC in 2009. I wanted to do physics and maths at university, so I enrolled in a Bachelor of Science at the University of Sydney, which took me 4 years to complete. Upon completion, I decided to do a Doctor of Philosophy, also at the University of Sydney. I started that last year, and it will take around 3 to 4 years for me to finish that. Basically, a Doctor of Philosophy is a degree where you just do research. So you're basically, you have some questions to answer, and those questions nobody in the world has the answer to. And so you're basically pushing the boundaries of knowledge for 3 to 4 years, and at the end of that, you kind of like find out a little bit more about the universe that nobody else knows, and so you get a PhD at the end of that. And I guess after that, there's a whole range of different things that you can do. You can continue on as a researcher and eventually become a lecturer and a professor, or you can go out and do all sorts of different things. So that's me. My research is seeking to answer 2 questions, one of which is what is dark matter, and the second of which is what is dark energy. So currently, we know that the universe is made up of 3 different types of matter or energy. The first is visible matter, which is just all of the different sorts of matter that we already know about, like protons, neutrons, electrons, and photons. But then there's also around a quarter of the universe made up of something called dark matter, which we don't really know much about. And on top of that, there's also something called dark energy, which we know even less about. So my research focuses on trying to figure out the properties of dark matter and dark energy. It's a huge research area, and there are lots of people in the world trying to figure out the answers to those questions, and they've been trying to figure out those answers for a long time. So hopefully at the end of my PhD, I'll be able to find out something which will help us understand a little bit more about the universe that we live in. Okay, so now we'll move on to your stuff. Today I'll be focusing on a successful rocket launch. The syllabus dot point says that this topic is basically about the different factors that we need to take into account to achieve a successful rocket launch, maintain a stable orbit, and also return to Earth. Because this dot point is very big in terms of like the amount of material that you cover, I won't be covering everything. I'll only be focusing on the 4 things that are listed on the slide. So the first would be the concept of escaping from Earth and escape velocity, and then I'll be looking at G-forces, followed by the rocket launch and the acceleration and G-forces associated with rocket launches, and then I'll be finishing off with a discussion of the challenges related to re-entering the Earth's atmosphere and how to overcome those challenges. So the first concept is the concept of escape velocity. So we all know that if we throw a ball up into the air, it will eventually come back to Earth. So we give it an initial velocity vi. So first we define the positive y direction as upwards, so that the acceleration due to gravity is defined downwards and is negative. And if we throw that ball up into the air, because of the acceleration due to gravity, it decelerates the ball, and so the initial Vy decreases in magnitude until it reaches a point where it is 0. And at that point, it reaches maximum height, and then it continues to decelerate, and so it falls down back to the Earth. And if we throw that ball with a slightly higher velocity, we know that it will reach a higher height before it falls back down. And if we extrapolate that idea a bit further, then we can think that then theoretically we should be able to, I guess, find a particular velocity to throw the ball so that it never returns to Earth. And so that's basically what escape velocity is all about. So on this slide, I've basically shown the concept of if you throw a ball to infinity, then that means that, if you throw a ball with a sufficient velocity such that at infinity the velocity reaches 0, it decreases to 0, then that ball will theoretically never return to Earth because you can never reach a distance of infinity from the Earth. And so the velocity at which you throw the ball so that the end velocity is 0 then corresponds to the escape velocity. So with that idea in mind, we can derive the expression for escape velocity. We start off with just the conservation of energy equation. So I have denoted kinetic energy with Ke and gravitational potential energy with Gpe. And what I've done is I've equated the total energy, which is the total kinetic energy plus the gravitational potential energy at the beginning, which is when you throw the ball. I've equated that to the total energy at the end, which is when the ball is at infinity. So we just basically write out the expressions for kinetic energy and gravitational potential energy. For the final kinetic energy, when the ball is at infinity, the kinetic energy is given by half mv squared, but the velocity is equal to 0 in this situation, and so the total kinetic energy is then equal to 0. Similarly, the gravitational potential energy at infinity is going to be equal to 0 because, well, first of all, the expression for gravitational potential energy, I don't know if you've already covered it, but it's written here. It's just equal to g, which is a gravitational constant, times the mass of the ball, which is little m, times the mass of the Earth, which is big M, and then divided by the distance that the ball is from the Earth, which is little r. So because the distance of the ball from Earth is infinite, if you put that into the denominator, the whole thing goes to 0, and so the total gravitational potential energy is 0. So that means that the right-hand side of the first equation is equal to 0. So if we just expand out the expressions for kinetic energy and gravitational potential energy on the left-hand side, then we have the following expression. We have half mvi squared, where vi is the initial velocity at which you throw the ball, minus g times little m times big M divided by ri, where ri is the distance from the center of the Earth where you throw the ball. So that whole expression equals 0, so all you need to do is just rearrange, and then you end up with this expression for the velocity at which you throw the ball. And that corresponds to the escape velocity. So just relabel the pronumerals. So this equation says that the escape velocity is inversely proportional to the distance from the center of the Earth. So that means that if you were to throw a ball further out from the center of the Earth, then the velocity at which you need to throw it so that it never returns to Earth is actually smaller than if you throw it closer to Earth. And similarly, it's also proportional to the mass of the Earth, which means that or the mass of the gravitating object, which means that if you were on the moon, for example, and you were to throw a ball at if you wanted to throw a ball so that it never returns to the moon, then you wouldn't need to give it quite as high a velocity as you would if you were to throw the same ball on Earth and try to make it never return to Earth. So that's what that equation is telling you. So the concept of escape, oh wait, yes, one more slide, sorry. So this is just another way of looking at escape velocity. So I've just stuck a red cannon, I guess, at the north pole of the Earth, and it's going to fire a ball. So I'm going to give it a smallish velocity, not enough to escape, so it just falls down to the Earth after it travels a little bit horizontally. If I give it a bit more of a push, a higher velocity, then it travels a bit more before it reaches the ground. If I give it an even higher velocity, it travels an even further distance before it reaches the ground. And at some stage I can give it a high enough velocity so that it never reaches the ground and it stays in orbit. And if I give it an even higher velocity, then it won't even stay in orbit, it will just shoot right out. So that's just another way of looking at escape velocity. So escape velocity is relevant to rocket science because in order to leave the Earth, you want to be able to give the rocket enough of a velocity so that it doesn't just return to Earth after you fire it out. It needs to be able to escape the Earth. So in this slide, I guess, well, we can't just fire rockets like from cannons. What we do is we kind of give the ability to push itself. We give the rocket like some kind of engine, and we have combustion happening in that engine. So we have like things like aluminium oxide or whatever, and then it reacts with oxygen, and then that creates a lot of gas, which is very energetic. And so those gases get exerted out of the backside of the rocket, and that means that the rocket essentially produces a force on the gas in the left direction on the screen. And Newton's third law says that every action has an equal and opposite reaction, so that particular action has an equal and opposite reaction that ends up being the force on the rocket by the gases. And that is equal in magnitude to the force on the gases by the rocket and is in the opposite direction, and that force is what is responsible for pushing the rocket upwards and onwards away from Earth. So I've written out an expression for the force of the thrust on the rocket, and it is equal to the velocity of the exhaust gases coming out the backside times the change in mass of the rocket. And the change in mass happens because as you're burning the fuel, you're losing mass from the total. You're losing the fuel mass, and so the total mass of the rocket decreases. And you divide that by the time over which that change in mass happens. So it's essentially proportional to the rate of change of mass. That's what the delta M on delta T means. But the important thing to note here is that the force of the thrust is also proportional to the velocity at which the gases come out of the rocket. And so that's actually significant because what you want to do is maximize the amount of thrust that you give to the rocket to accelerate it maximally. And so you need to figure out a way to design the rocket so that you can actually maximize the velocity at which the gases shoot out of the rocket. Okay, so another thing to take into account when you're doing a rocket launch is the fact that the Earth already has its own motion. So the Earth does its own rotation, and that means that there is a tangential velocity at each point on the sphere, except for at the North and South Pole, which is the axis at which it is rotating. So what that means is that, that if you fire a space shuttle, say, from a position on Earth, the space shuttle will have its own velocity relative to the Earth, but it will also have a boost due to the Earth's rotation. So the concept is very similar to if you were riding a bike, say at 20 kilometers an hour, and you threw a ball at 5 kilometers an hour relative to yourself. Somebody standing on the side of the road will see that ball being thrown at a velocity of 25 kilometers an hour. So you just add the two velocities. The same concept is happening here. The rocket gets an extra added velocity because of the velocity of the Earth already as it's rotating. So this is something that, that rocket scientists do take into account. For example, NASA fires its rockets out from Cape Canaveral, which is close to the equator, and the reason they do that is because at the equator the tangential velocity is greatest, and so the boost that the rocket gets is also the greatest as well. So they're taking advantage of that the best that they can. The second motion that can be taken into account is the orbital motion of the Earth. So when the Earth is going around the Sun, it's got an orbital velocity relative to the Sun, and again, you can use that velocity to boost the velocity of the rocket relative to the Sun and all the other planets as well. So now we move on to the concept of G-forces. I think most of you will have heard of G-forces. What they refer to is basically how much force you feel on yourself in terms of the acceleration due to gravity on Earth. And if you're looking at vertical G-forces, then what it corresponds to is your apparent weight, which is what you would read on a bathroom scales, divided by your true weight, which is just your mass times acceleration due to gravity. So what do I mean by your apparent weight? Why would your apparent weight not be equal to your true weight? Well, for the first example, we can imagine somebody, say, jumping on a trampoline or on a bed. So there is a point when they're not touching the bed, when they're just falling towards the bed or the trampoline, and at that point, the only force that is acting on them is due to gravity, it's due to their own weight. There is nothing else resisting their fall, and so they feel weightless. So the apparent weight is 0, even though their true weight is mg. I don't know if you've ever tried this, but you can try jumping up, and there's a brief moment where you feel pretty much weightless if you ignore air resistance. So on the right, I've basically written down how you would work out the G-forces for this situation. You just start off with the weight that you feel, which is the apparent weight, which is 0, and then you divide that by your mass, which is again 0, and so the G-force then is equal to your weight per unit mass divided by G, which is 9.8, and that is also 0. So in this situation, the total G-force on you is 0. in the next example, we have somebody standing at rest on the ground. And because they're at rest, it means that they must have zero net force on them. So the only two forces acting on them are due to gravity, so their own weight, mg, acting downwards. But the ground also exerts a force on them as well in the opposite direction. And that force is called the normal force, and it is also equal to mg. So the reason that force exists is because the weight of the person is exerting a force on the ground, and so by Newton's third law, the ground has to exert a force of the same magnitude in the opposite direction on the person. And so that means the net force on the person is just mg minus mg, which is equal to 0, which is why they're at rest. But the key point here is that the person feels a resistance due to the ground, and so that corresponds to their own weight. And if they were to stand on some bathroom scales, they would realize that the bathroom scales actually shows their true weight. So that means in this case their apparent weight is equal to their true weight. The weight they feel is mg, their weight per unit mass is then g, and so the g force that they feel is just 1. In the third example, we have somebody who is in an elevator accelerating upwards with an acceleration given by a. So in this case, there is still a force of gravity acting downwards on the person, and so the ground of the elevator, the floor of the elevator must also exert an equal force equal to mg on that person, but opposed, like in the opposite direction. But the person is not at rest, the person is accelerating upwards, so the floor must also exert an additional force equal to m times a, which means that the total force the person feels from the ground is equal to ma plus mg. And so the total weight that they feel is ma plus mg, the weight per unit mass is then a plus g, because you just divide by m, the g force is then a plus g divided by g, which is just a on g plus 1, where a on g is the g force felt by the person due to just the acceleration of the elevator, and 1 is the g force felt by the person due to their own weight, which is always there. So in this case, we find that the normal force that the person feels is actually bigger than their true weight, which is mg. And so I think, like most of you probably have been in an elevator where you're going up, you actually feel a bit heavier than you normally do. And conversely, if the acceleration was going downwards, then it would have a negative sign. And so the normal force that the person feels would be equal to mg minus ma, which is less than their true weight. So they would feel a little bit lighter than they normally do as well. So now we move on to the stages of a rocket launch. On the bottom right, I have a graph showing the g-force variation for astronauts inside a rocket with time. And in the next section, I'll just basically be taking you through that graph, basically explaining why the g-forces are changing as they do with time as the rocket launches upwards. So the first stage of the rocket launch is liftoff. And at this stage, as I said before, the rocket ignites its engine, combustion happens, and it produces gas out its backside. Newton's third law then means that the rocket has to experience a force from the gas that's pushing upwards, and so that accelerates the rocket upwards. And because there is an acceleration upwards, the total g-force has to be greater than 1, just like in the elevator example we were looking at before. And so what we see is between A and the first dot point, we see a straight slope from g-force of 1 to a g-force of almost 2, where the rocket is continually accelerating, and so the g-force is continually increasing as well. But then after that, we see a decrease in the g-force because they deliberately reduce the amount of thrust applied to the rocket in order to reduce the amount of air resistance that they're pushing up against. And the reason they do that is just to save fuel. So they do that until the atmosphere is thin enough for the air resistance to be much less, and so they can reapply their thrust and then increase in acceleration again. And so that's what's happening between, say, a time of 50 seconds and between point B. And then after point B, what actually happens is that their fuel starts to run out. And so the thrust decreases a little bit again, which means that the acceleration of the rocket upwards decreases a little bit, and that means the g-forces decrease as well. And then it keeps decreasing from point B to point C as the fuel starts running out. And then what they do next is they drop some mass from the rocket. So I should have explained this before, but essentially for a space shuttle or any spacecraft, there is not enough room inside the spacecraft for all the fuel that is required for the journey to be held. And so what they need to do is they need to attach an external fuel tank to the spacecraft. So in the bottom left-hand corner, there's a picture of an external fuel tank. It just contains the fuel for the shuttle, and because the total weight of the shuttle and the external fuel tank is quite large, they need to add on extra rocket boosters in order to help thrust it up. And so those are what those two little rocket things are in the top left-hand corner. So after the fuel in the rocket boosters runs out, they drop those boosters, and that means that the mass of the rocket is decreasing. And if you apply the same force, you keep the same force applied to the rocket, then because the mass is decreased, the acceleration has got to increase. It's just from F equals ma, and so that's what's happening beyond point C that we see here. And then somewhere between point C and point D, so after point C, because the mass has decreased, the acceleration then increases again, the G-forces increase steadily. And then between point C and point D, they drop the external fuel tank, and then that increases the acceleration of the rocket even more. And so they basically increased their total G-force to around 3 Gs, but at this point they decide to reduce the thrust again, because they don't want to subject the astronauts to G-forces greater than 3G, because basically 3G feels like you're 3 times as heavy as you normally are, and it's pretty uncomfortable. And humans can only take a limited amount of G-forces. So they don't let the amount of G-force increase above 3, and so what happens is they just reduce the thrust, and at that point they're already nearing their orbit, so their game plan is to get into an orbit. So what they do is they just keep reducing the thrust until they kind of ease into the orbit, and so that's what we're seeing between D and E. The acceleration is decreasing because the thrust is decreasing, and so the G-forces decrease until they reach point E, where they're essentially in orbit, and the total G-forces they feel are 0 because there's no acceleration. Sorry, yeah, there's like, the only acceleration is due to Earth, and there's no resistance, so there's no G-force. Okay, so that's basically like the whole rocket launch, and it's interesting to note that it takes like 500 seconds, which is less than 10 minutes. I think like if they want to go into higher orbits, it might take an extra 45 minutes to get to that point. And in order to get to this point, they use up quite a large percentage of the original amount of fuel that they have as well. Okay, so now we'll just go through a brief overview of orbits, because I just mentioned that, that when you're in orbit, the G-forces are 0, so I thought I should probably explain that a little bit more. So here I have a picture of a red projectile, a red ball, in orbit around the Earth. It travels along the path indicated by the orange or yellow circle, and the velocity of the orbit is a tangential velocity that is perpendicular to the force due to gravity, which I've drawn with a green arrow. That force due to gravity is always directed towards the Earth, the center of the Earth, and the velocity of the orbit is always perpendicular to that, and is always tangential to the circle which forms its orbit. So the key point with an orbit is that the orbital velocity is very high, and so what happens is it's high enough for the red ball, in this case, to actually travel quite a large distance off to the right on the screen. So I've indicated that distance with the blue arrows. So what happens is the gravity due to Earth tries to pull the red projectile down, but in the meantime it has a sufficient horizontal velocity to get it out to the side, and by the time it gets there, the Earth's ground has already curved away, and so it doesn't end up meeting the ground. And that's essentially what's happening all the way through the orbit. It's basically always falling towards Earth, but it's going so fast in the tangential direction that it never reaches the Earth because the ground curves away before it can. And so in orbit, essentially, it's just like being in free fall. You're always falling towards the Earth. The only forces that are acting on you is the force due to gravity. And so that's why when you look at pictures of people in the International Space Station, they're always floating because they're always in free fall. So on the top right, I've written the equation for the orbital velocity. It's equal to the square root of the gravitational constant times the mass of the Earth divided by the radius, or the distance between the orbit and the center of the Earth. And you can actually derive this pretty easily as well, just by equating centripetal force to the gravitational force. But the key point with this equation is that, again, when you have higher orbits, so the distance between the orbiting projectile and also the center of the Earth, when that is large, then the orbital velocity is small. And when the distance is closer to the Earth, then you have a larger orbital velocity. So satellites that are closer to the Earth actually travel faster than satellites that are further away from the Earth. But another key point, I think, which is worth mentioning, is that the orbital velocity doesn't depend on the mass of the satellite at all. So I think this is not really that surprising because we know that it's like being in free fall, and we all know about the Galilean experiment where he drops like a feather and a cannon down the Tower of Pisa, and I think we've done these experiments before in vacuum where there's no air resistance, and when you look at what happens, they both fall at the same rate even though they have different masses. And so the same thing is basically happening here. Two satellites with different masses will also fall at the same rate, and so the orbital velocity doesn't actually depend on the mass of the object in question. So the last topic that I'll be talking about is re-entry, which is basically the process of the space shuttle or spacecraft re-entering the Earth's atmosphere, and we want to make sure that that the re-entry is safe whenever we want to recover some parts which are on the spacecraft or when there are astronauts on board. So there are a couple of things that we need to think about in terms of re-entry, because the whole process is quite dangerous. If you enter at an angle which is too steep, so in the undershoot boundary on the slide, if you enter in that region, then what happens is the amount of drag that you experience as you go through the atmosphere is going to generate too much heat, and that ends up incinerating you, or basically disintegrating the spacecraft, which is not good. But conversely, if you were to enter the atmosphere at an angle that is too shallow, so in the overshoot boundary region, then what happens is you have too much lift and you end up glancing off the top of the Earth's atmosphere. And that's pretty terrible if you don't have enough fuel to try another re-entry. So basically there's only a very small corridor called the re-entry corridor, a small range of angles at which you can enter the Earth's atmosphere so that you don't burn up and so that you don't glance off the atmosphere. And so that's what everybody needs to try and find when they're trying to re-enter the Earth. But even if you make it through the re-entry corridor, there are still other issues to worry about. So the main issue to worry about is the fact that when you go through the atmosphere, you're basically, I guess, at a high velocity, you're basically shooting through the atmosphere and creating shock waves. And those shock waves generate a lot of heat, and that heat is what is the dangerous thing. So it's the same thing. It's the same thing that actually causes asteroids to burn up in the atmosphere when they kind of like go through the Earth's atmosphere. On the left here we have the traditional teardrop vehicle, which was used by NASA during the 1960s and 1970s. And on the right here we have the space shuttle, and we're seeing two images of them both re-entering the Earth's atmosphere. So on the left, what we see is the teardrop vehicle oriented with the blunt side entering the atmosphere first, and that's something that needs to happen because if you enter the atmosphere with the sharp side first, then you end up creating a shock wave that kind of borders the spacecraft, and that means the heat generated is very close to the spacecraft, and so it's much more dangerous, and it's much more likely that the spacecraft burns up in the atmosphere. And so what you need to do is you need to enter the atmosphere with the blunt side first, because the shock wave shape that is created there is kind of a more gentle curve, and so it doesn't actually hug the vehicle very much. It only affects the blunt side of the vehicle, so the rest of the vehicle is kind of like more protected from the heat. And the same thing happens with the shuttle. You want to enter with the blunt side first as well, so that the top side gets protected from the heat. But even with that protection, it's also important to have other things like heat shields, because the temperatures that can be reached can reach up to, I think, like 1,500 degrees Celsius upon re-entry, and that's it's really dangerous. And so what you need to do is you need to have special materials coating your spacecraft, special materials that are highly insulating, so that the heat outside does not get transferred to the cabin inside. And those materials also need to be pretty high in melting point and boiling point. And sometimes, especially with the teardrop vehicles, you also need to have materials that are designed to evaporate or erode due to heat. So the process is called ablation, and it's the same process as when you sweat and the water on your skin evaporates and takes away the heat from the skin as it does so. In this case, we have a special material coating around the spacecraft, and it evaporates or erodes away, and it takes away some of the heat as it does that. The other thing to think about is that to notice is that when during re-entry, when the amount of heat produced is very high, the air molecules actually ionize, which means that the electrons get ripped off the molecules and the atoms. And so what you end up with is a bunch of charged molecules and atoms and a bunch of electrons called a plasma. And that plasma prevents radio waves from penetrating through them, which means that during re-entry, the people on board the spacecraft can't actually communicate with people on the ground. However, in the case of the space shuttle, the top part of the space shuttle doesn't really have that much, like the ionization is localized to the bottom part, and so what they do is they fire radio waves out the top part, and they communicate via a satellite. So it hits the satellite and redirects down to the ground, and so they can still communicate with people on the ground. But otherwise, if they didn't have that, then they wouldn't be able to communicate at all during re-entry, just because radio waves can't penetrate that plasma. I think the last thing to say is that with the teardrop vehicle, they tend to kind of like enter the atmosphere very quickly, almost like ballistically. And because of that, they need extra parachutes during their re-entry as they fall to the earth in order to slow them down. Otherwise, they'll just crash when they hit the ground or when they hit the water. In the case of the space shuttle, they don't need things like that because the space shuttle has a lot more control over the lift. And so they can kind of like, I guess, ease down into the atmosphere a lot more than the teardrop vehicle can. And what they do is they end up landing on a runway, and when they're running on the runway, slowing down, they then fire out parachutes in order to slow down their horizontal motion. So that concludes my talk, actually.